this section, this topic, we're going to discuss calculus. And calculus is where everybody sort of, for some obscure reason, gets the trembles and thinks it's exceptionally difficult. Yeah, once you start getting to university second year, it gets a bit complicated. But you know what? As long as you just keep your head about you with the recipes, and obviously there's going to be some little tricks of the trade we're going to bring in, it turns out that it's actually quite a good section of the work, because it's predicated on following a set of sequences that we're going to do. Now, let's just start off, and you will see that it's either going to be called calculus, also differential calculus, yes. Okay, so what we're going to do is we're going to just, first of all, we're going to just recap something. If I give you f of x equal to x squared plus 2x minus 3, you know that that's a parabola pointing that way, and you know that it goes through at minus 3. It cuts the y-axis. Now, what we're now going to do is we're going to look at this and we're going to say, okay, then please tell me what is f of 2, right? F of 2, we said, is wherever we see an x, we replace with a 2. And you use brackets, right? So f of 2 turns out to be 4 plus 4 minus 3, which is equal to 5. Please also remember that f of x is equal to y. It's the same thing, right? We've just said it's a function of x, it is y. It's just the definition that we're using. Next, I'm going to say to you, then what is f of 4? You will say it is 4 times 2 plus 2 times 4 minus 3, and the value there is going to be 21. All I did is wherever I saw an x, I replaced. So what is f of x plus 1? Once again, it's wherever I see in the original squared plus 2 times x plus 1 plus, minus 3. Minus 3. Can you see what I did? All I did is I just replaced the x squared and the x with that. That's all I did. In all of these, that's all we're going to do. So therefore, if I said to you, okay, then what is f of x plus h? Never mind at this stage what that means. What is it? What do? I say, right, that's x plus h all squared plus 2 times x plus h minus 3. And then I multiply that out. The first one is x squared plus 2xh plus h squared plus 2x plus 2h minus 3. Okay, and maybe I can simplify that as well. So all in all, what I've got here is I've got an f of x, and we've just recapped some of the ways that we're going to be substituting in for the x. Wherever I see an x, I replace it with what's in that bracket. Just let's recap a couple of other things. Remember slope. Slope of a line is y is equal to mx plus c. This is a straight line. That's a straight line. And this is the gradient, aka slope, is it not? That's the gradient and it's the slope. And you know m is equal to y2 minus y1 over x2 minus x1. I have previously written it as change in y over change in x. Delta means change. Those of you who did physics with me, you'll have seen it that we use it a lot. Delta T, change in temperature. Okay, so now we're going to go and we're going to look at a simple example first of all. And don't worry, we're building up to getting to what this whole process of differentiation and calculus is all about. Okay, let's see. I'm now going to say, what about the graph y equals x squared? Right? What is f of 2? Well, f of 2 is equal to 2 squared, which is 4. F of 4 is equal to 4 squared, which is 16. Now, if you remember, if I drew this graph over here, just very quickly, I'm going to draw it. And I know that it's not going to be perfect. Straight away, it's not, because I got it wrong on the inward slope. I'm just going to draw a graph that looks like this, like so. And I am going to say that over here, I've got x equal to 2, which means that's going to be f of 2. F of 2, we've just said, was 4. And over here, I'm going to say that this is x equals 4. And I'm going to put there f of 4 equals 16. I think everybody's quite happy with that. I could also do f of the other side. I could do f of minus 2, f of minus 2, and f of minus 4. And they come, I'll change color, they come to be exactly the same number because essentially we're squaring it. Just prove that. Put in f of minus 2 is minus 2 squared, which is equal to 4. F of minus 4 is minus 4 squared, which is equal to 16. So there's our number, 4 and 16. We've got them. I want you to just for a second consider something with me. I want to see, what is the slope of this line? Whoa, hold on. How do I do the slope? Slope is change in y over change in x. Let us call this point A and that point B. If I join that up with a straight line there, I can work out the slope, can't I? Delta y, delta x. I can then work out what the slope is from A to B. Ditto, I can work it out if I had here A prime and B prime. Can you see I'm going to get a straight line joining those points. So let us work out what the gradients are of those points. Okay, you've got it on a piece of paper. So I'm just going to say, right, the gradient is going to be, m is going to be y2 minus y1 over x2 minus x1. And let's start getting used to delta y over delta x. Let's just look at it in terms of change. So therefore, it's going to be equal to 16 minus 4 over 2, which is equal to 8 over 2, which is equal to 4. Similarly, I can do it the other way, and I can say that my gradient is going to be negative. Okay, we'll get to those in a sec. Or rather, let's do it. Let's do the gradient on the other side. M, this is now between A prime and B prime, is going to be equal to 16 minus 4 over minus 2, right? Which is going to be equal to minus 4. Is that right? Okay. 16 minus 4, okay, is to 6, you sausage. Sorry, guys. Okay. 8 over 2, sorry, it's 12 over 2 is 6 and minus 6. Eish. And here I am doing math. 6 and minus 6. I'm looking at something that's got a 4. That's why I checked myself. So 6 and minus 6. Right? All I've done here is I've gone, let's go back to the curve. Let's go back to the curve here. I've worked out, can you see that over here, okay, delta x was equal to 2. Delta x here is minus 2, is it not? The difference is minus 2. Minus 2 gets me to minus 4, does it not? Therefore, my delta x is that, and my delta y over here was equal to 16 minus 4, which is equal to 12 units and 12 units up. So that's where I got those numbers from. So we've got 6 and minus 6. The interesting thing to note is that, just very briefly, the gradient, the slope, this side is plus, this side is negative. Why? Is because it's going down here and it's going up there. We're going to get to this point over here where we've got a turning point. That's where we don't have a slope. Slope is 0. But we'll get to that. So we've got that. The next step is to say, all right, we've got that, the negative average. Now we call this the average gradient. This is called the average gradient. That's what we term this. It's the average gradient from A to B. What is the gradient actual? Now I want to just zoom in for a second. I've got a thingy here where I want to zoom in. This is at, oops, let me just try and get it a bit more accurate. It's quite difficult working on these tablets. X equals 4 and X equals 2. Remember we had over here, this was going to be equal to 2 and 4. This was going to be equal to 16 if I'm not right. This was 4. And we had the whole concept of delta y and delta x. That's the average gradient was between those two numbers. The line joining those two, like that, okay, is called a secant. Secant, joining those, going through there. But I only want the gradient at 2. Let's look at this line at 2. What am I saying is I actually want, this is the tangent. I want to know what is the actual gradient at x equals 2. Because I can see each time it's changing, the gradient is getting steeper. The slope of the tangent is getting steeper as I go up the parabola. And that's going to be for any curve, it's going to be changing. But I want to know what is it there. This is the actual gradient at x equals 2. Therefore, I am actually looking for the slope of the tangent at x equals 2. That's what I really want. The slope of this line, the tangent at that point. That's my objective. It's what I want. Now, we have a bit of an issue now because we've got to find somehow of working that out. So obviously, I could say, all right, let us now put in, just let me change to green, for example. Let's put in here at x equals 3. Therefore, that's going to be 9. So therefore, now I've got, can you see the green one is now going to be 9 minus 4, which is 5, is delta y. Delta x is equal to 1. Therefore, the m now is going to be equal to 5 over 1, is it not? It's going to be 5. Remember, it was 6. Now, that's there. But what if I put in the next one, and let's call that blue, at x equals to 2.5? Right? You can see all I'm doing here is I'm making delta x is now 0.5. Is it not? And if I put in 2.5, I end up with 6.25. 6.25. So I say therefore the average gradient here is going to be 6.25 minus 4. Can you see there? Divided by 0.5, and my answer comes out to be 4.5. 6 to 5 to 4.5. And if I keep making this little delta x here smaller, 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 I'm starting to get to that point. So let's examine it in terms of a sketch, and let's get to the bottom of what this is all about. I'm going to draw in here once again a zoomed up portion. There we go. And here we go. Just for example, I am saying this is x. And this little distance that I'm adding on over here, I am going to call h. Remember, this was actually delta x. All right? Therefore, the coordinate is x there. This coordinate is x plus h. Right. Then I can go, and I'll use blue. I say this coordinate over here, it's doing its saving. That coordinate over there, that's a bit of a sort of a mucky bit. Let me change it. The coordinate there is going to be f of x. That's the y, isn't it? So what's the top one? This is going to be f of x plus h. So thus, delta y is actually going to be equal to f of x plus h minus f of x, y2 minus y1. That's all it is. And delta x is going to be equal to h. Delta x is going to be equal to h. That's all I've said. Let's have a look. Okay. Now let's have a look. What is our gradient? Right? You guys have got that. You've drawn it. Stop me with these and draw these things, and then we'll continue with it. So therefore I say, right, the average gradient m, I will go back to black if you will forgive me for doing so. The average gradient m, in other words, it's between there and the line above, correct? Over here. The average gradient of this the average gradient of that is going to be equal to m, which is essentially delta y over delta x, or y2 minus y1 over x2 minus x1 if you prefer. y2 was f of x plus h minus f of x, all divided by x. X plus h minus x. Correct? Which turns out to be f of x plus h minus f of x all over x. This comes out to be x plus h minus x, which is h, which is what we expected. All I've done there is done it a little bit rigorously. Okay, so let's just move this back up slightly. Right, so we've got that. Now, what we're saying is this h here, right? H is a small number. So first of all, we could have h could be equal to 0.1. Therefore, it's going to be f of 2.1 minus f of 2. But we could also go f of 2.001 minus f of 2. What about f of 2.000001 minus f of 2? Can you see that here h is getting smaller? That little increment that we're stepping up is getting smaller. So what do I really want? I want h equal to 0. I want h equal to 0. Therefore, I then get the slope or the gradient at the exact point I want. This is where we are. So essentially, the slope is equal to that, and we're now going to have a problem because I'm saying that the gradient, let me go back up to my gradient formula. My gradient is this. But what if h is equal to 0? We've got a problem. We can't make h equal to 0 because that won't let us. So we now have to bring in a branch of mathematics, and we say, all right then, let's pretend h is tending towards 0. So we're going to look at it. We're going to look at it as h tends to 0. Tends to 0. In other words, h gets less and less each time until it's 0, if we can make it equal to 0. This is the question we've got to look at. Well, how do we do this? We then say, we write down, the first thing is, this is called the limit and the derivatives. We're going to now actually define limits and derivative. I guess it comes from, that it derives from. I guess that's what Newton had in mind, or whoever other maybe qualified what it was. Pretty sure it was Newton though. But anyway, we now say the derivative is f prime of x, and it equals the limit as h tends to 0 of f of x plus h minus f of x all over h. That is what it is. So therefore, the derivative, this piece here, this derivative, the derivative is the slope or the gradient of the tangent to a curve at a specific point. Only a specific point. Because remember, the slope is changing depending upon the curve. The slope of a straight line is constant. We are going to see that in a few moments. How do we set about doing this? Well, let's do a few examples of these, okay? This is the recipe that I put forward to people to use. Obviously, you develop your own, but I find this works well because I just don't get confused. I find if I have too much in the numerator, it gets confusing and it's prone to errors. So I like the simple methods. Keep it simple, stupid, that way of doing it. Let's just make sure we're on. Let's do a few examples. Find the slope. Here's an example. Find the slope of the graph, curve, or function at x equals minus 3. And they say it is f of x equals x squared. What do? First thing I'm looking for is I am looking for the limit. I am looking for this elusive character. The derivative equals the limit as h tends to 0 of f of x plus h minus f of x all over h, aren't I? Now what I do, it's the same concept as I do when I do the cubics. If those of you who did cubics with me and who are still going to do some more of them, I like to split it and I say, okay, this is my working area. I say, right, what is f of x plus h? It is going to be x plus h squared. And f of x itself is going to be x squared. Doesn't matter if you put them the other way around, really. Just then say to yourself, my next step is then work out what is f of x plus h minus f of x. What am I doing? I am working out the numerator. I'm calculating it here just to make it simpler for myself. Okay, so I don't get confused. That then is going to be f of x plus h, which is x plus h. Now I haven't simplified. This is why I like this. This is thus going to be x squared plus 2xh plus h squared minus x squared. Now we remove the brackets. Okay, I'm just going to pull that back up so that we can see it. There we go. So I now remove the brackets and I say that is then equal to x squared plus 2xh plus h squared minus x squared, which becomes 2xh plus h squared. Now I say that f prime of x is going to be equal to the limit as h tends to 0 of 2xh plus h squared over h. What did I do now? Sorry, what did I do? Let's pull it back. I just substituted what I got into the numerator. I just substituted into numerator. That's all I did. I worked it out simply. I really must change that. I worked it out, right? I worked it out here, okay, and I simplified, and then I substituted into the top. Now to continue. Okay, I can go back to the black. This is the limit as h tends to 0. Now you must write this each time until you put h equal to 0 when you can. I can't put h equal to 0 because it'll be undefined. Therefore, I have to say, and here's the trick, you factorize the top. H comes out, leaving us with 2x plus h over h, which is the limit as h tends to 0 of, that cancels out, 2x plus h. Now, h equals 0, what happens? I can actually put it in. I say that's going to be 2x plus 0. So basically my answer is 2x. So the slope of the line, the tangent, at any point to that curve is 2x. I was asked at minus 3, therefore I would say therefore the gradient or the slope, the gradient of the tangent to f of x equals x squared at x equals minus 3, you would have m, and I'm going to tell you I always do this, tangent, okay, I say m is equal to 2 times minus 3, which is minus 6. Because we're going to be asked the equation of the line, which is the next one. So what is the equation of the tangent then? Well, the equation of the tangent is equal to y equals mx plus c. Always a straight line. Why? Because that's the definition of a tangent. It touches it at that point. It's a straight line that touches it at that point. Now, you can have surfaces that are tangential to each other. So if I've got a ball and a piece of paper, it's going to touch it at one point, isn't it? That's a surface that's tangential. I thus now have a situation where I say the equation of the tangent is that. What do I know? I know that then y is equal to minus 6x plus c. Now what? Just remember, what point did it go through? What point on f of x equals x squared did it go through? It went through the point x equals minus 3. Therefore, y is going to be minus 3 squared, which is going to be equal to 9. Therefore, it went through minus 3 and 9. Whenever you are given an x or a y value of the original function, you work out the corresponding one. And that then gives you your point through which it goes. Thus, I can say that this is x and that's y. Therefore, 9 must be equal to minus 6 times minus 3 plus c. And basically, I can take it from there and I can say that 9 must be equal to 18. 3 6 is 18. Let me just check myself. 3 times 6 is equal to 18, which is plus c. Therefore, in this case, 9 minus 18 is c. Therefore, c is going to be equal to minus 9. Thus, the equation of the tangent is y is equal to minus 6x minus 9. That is it. And from then on, you can do anything with that if you like. We're going to do a few more from first principles. But what do? We always write down the formula the derivative is. What's our key words? If we see from first principles, we do it this way. We're going to get to relax. There's a recipe. There's rules for doing this. You don't have to do this every single time. It's not necessary. We've developed a whole series of rules to differentiate and the opposite, to integrate many functions. And it's actually quite simple to follow the rules. So no, we don't have to do this every time. Now, thus, in the next lot, when we get to the examples, I'm going to stop here. I can't do any more. Okay. The other key words is if we see things like tangents and another word, the normal, we're going to look at him in a few minutes as well. So when we see those, we are looking at derivatives. All right. That is what we're talking about here. Cheers. I'll see you in the next one. The next one, we're going to do more examples of some more complicated ones from first principles. And then we're going to start developing a set of rules to follow out and do differentiation of virtually anything that you're going to be given. Cheers. I'll see you later. Have a good one. Bye.